Watch this motion, a simple weight on a string swinging back and forth in a constant hypnotic rhythm. Yet this unassuming device hides a complex interplay of forces, prompting us to ask what exactly controls its precise repeating rhythm. The defining characteristic of that rhythm is its period. This is the exact amount of time the pendulum takes to complete one full cycle, swinging from left to right and back again. To understand what dictates that time, we can manipulate three physical variables in the lab. We can change the weight of the swinging bob, which is the mass. We can change the width of the swing, known as the amplitude, or we can change the length of the string. By systematically isolating each of these three variables and running them through independent trials, we can decode the invisible forces that govern both motion and time. We begin our trials by testing mass. If we compare a very light pendulum bob side by side with a much heavier one, the intuitive assumption is that the heavier object should swing faster, since gravity is pulling down on it with greater force. But when both are released, the result is unexpected. The heavy pendulum and the light pendulum swing in perfect synchronization, keeping absolutely identical periods. This happens because of inertia. It is true that gravity pulls harder on the heavier bob. However, because it is heavier, that mass inherently resists being moved to the exact same degree. The increased gravitational pull is perfectly balanced by the increased resistance to movement. This mathematical cancellation ensures mass plays no role in the speed of a free-falling pendulum swing. Next, we test amplitude. We pull the pendulum back to a shallow 10-degree angle, release it, and then repeat the exact process at a 20-degree angle. The time period is identical for both swings. This phenomenon, famously observed by Galileo, is known as isochronism, meaning equal time. This chart shows the pendulum's displacement plotted over time for small angles. It forms a smooth, predictable sine wave, because the restoring force pulling the bob back to the center is nearly linear. This is known as the small angle approximation. When we pull the bob back to an extreme 60-degree angle and release it, the predictable math starts to fail. At this height, the period actually changes. The simplified model breaks down because the restoring force is no longer proportional to the angle, requiring complex calculus and elliptic integrals to accurately predict the motion. While pendulums are often taught as perfect harmonic oscillators, large angles reveal the divergence between physical forces and our simplified mathematical models. For our final trial, we test length by comparing a pendulum on a very short string to one on a much longer string. Here, the difference is massive. The longer the string, the exponentially slower the swing, resulting in a much longer overall period. Gravity pulls straight down, tension pulls up toward the pivot, creating a restoring force toward the center. These vectors reduce to one master equation. T equals 2 pi times the square root of L over G, proving period depends solely on length and local gravity. Because mass is irrelevant and amplitude is negligible at small angles, the rhythm of a pendulum is a physical manifestation of length and local gravity. This equation had massive practical implications. By controlling the exact length of the string, you can lock in a highly predictable period, giving you a reliable way to measure time. In 1656, Christian Huygens used this math to build the first pendulum clock, providing a level of precision that defined timekeeping for over 250 years. Later scientists inverted the logic of the equation. If you know the exact time of the swing and the length of the string, you can calculate the strength of the gravitational pull beneath your feet. Researchers developed the seconds pendulum, designed so each half swing took exactly 1 second, and traveled the globe to take precise gravity measurements using Henry Cator's reversible pendulum. These pendulum measurements provided the first physical proof that the Earth is an oblate spheroid. Because gravity was slightly weaker at the equator than at the poles, researchers realized the planet was actually bulging in the middle. Scaling far beyond simple clocks, pendulum physics continues to measure the forces of the planet in modern scientific applications. A seismographer relies directly on pendulum principles and inertia. While the Earth moves beneath it, the suspended mass stays stationary, which allows the instrument to record the vibrations of earthquakes. Perhaps the most monumental demonstration of pendulum physics was used to prove the rotation of the Earth itself. A Foucault pendulum consists of a massive weight swinging on a very long wire. Over 24 hours, it knocks down a circle of pins as the Earth turns beneath it. From basic clocks to mapping the globe and detecting earthquakes, this single physical mechanism remains an essential tool for scientific measurement. A weight swinging on a string demonstrates how a simple mechanical arrangement can reveal the rigid physical constants that define our world.